So till now, we discussed the FIR and the IIR filter and obtained its transfer function of the generic FIR filter and the generic IIR filter. However, let us kind of discuss this a bit more, and so that we can consolidate on how to go about obtaining the transfer function of any given filter in the digital domain and also for implementation. Let me just discuss on this aspect, taking a smaller example. Let us take a first order filter example and see how it works. So I will take a unit delay block like this. I'll take a unit delay block. I'll give the input discrete signal stream here, UN. I will tap off from here, pass it through a scaling factor, A0 as usual, and I'll tap off from here after the delay, pass it through a scaling factor A1 and give it to a summer. I'll give this one also to a summer, and the output is Y of n. Now this is your first order FIR filter. Now we know how to get the transfer function of this, right? You say that what is YZ? YZ is equal to, so U of Z, the Z transformed value of the discrete signal passing through A0 comes to the output. So A0 UZ plus A1 into UZ into Z to the power of minus 1. This is the transfer function. A bit more intuitive. So let us have a bit more intuitive feel. Let us take a snapshot at an instant of time. So if you take the x-axis is the n axis, the discrete time axis, and I am going to divide it into equal parts, and these equal parts are based on the sampling period, right? So several of them, and then I will take these three general points here. Okay, these three general points in time. What are the sample points? So if I say this is KT, right? This is 0, 0t, 1t, 2t, so on. So this is KT. So what is this going to be? K minus 1t. So if this is the kth sample, this is K minus 1th sample, and this is going to be K plus 1th sample or K plus 1t, where t is the sampling time. This is 0, 1, t, so on. Now let me take the snapshot at KT. Let's say KT is the present. KT is the current time of interest. So at this moment, what happens? So if you take the snapshot of this at KT, then Y, at that point in time, the value of Y will be Y at KT. And the input at that point in time will be U at KT. So in the literature, you will see different ways of writing it, the nomenclature. So because T is the sampling time, it is understood that T is there. People may write it as Y of K or kth sample, Y at kth sample, right? And I can still simplify that in writing and say Y subscript K, which means that Y at kth sample. Imagine. Likewise here you will see that U in parenthesis K implies kth sample of U, and I can write it in a much more simpler manner as U of K subscript K, which implies that it is the kth sample of U. I prefer to use this notation, the subscript notation, easier to use. So if this is u of k or the kth sample of u, what is available here is the k minus 1 sample of u, which is u of k minus 1. So now let us write the equation for yk. Yk is, look at this, a naught into uk plus a1 into uk minus 1. So uk minus 1 is nothing but uz into z to the power of minus 1, unit delayed version of uz. So that is uk minus 1, the previous sample. So this is a much more nice and elegant way of representing a signal. This is at a snapshot of k. At a snapshot time interval of k, this is the equation. And this is the transfer function. For transfer function, you have to use the z variable. So let me push this aside. Let me now include the feedback part, the IIR filter. So I am going to feedback y through a unit delay and a scaling factor. This is z to the power of minus 1. So this is moving in this fashion. The signal B1. So this is the feedback part. So I am just only looking at first order so that it is much easier. Now write the equation for yk. So y of k equals, so this one, a naught into u of k plus a1 into u of k plus b1 into this value. What is this value? This value is y of k. This is a unit delay component, so this is y of k minus 1. So b1 into this y of k minus 1. So that is the constitutive equation, snapshot at, if I take it with respect to a snapshot at kt. Now if you see that, you see here, the polynomials, if this is a polynomial in z, the coefficient of the polynomials or the terms in the z domain or the z transformed equation, and that in the time or the n equation at kth with respect to the kth interval of time, the coefficients are all same. So it is easy for me to move in and out of the time domain and the z domain, n domain and the z domain. So yz is nothing but, yz is, I will put the same coefficient, uk is uz, a1, uk minus 1 is uz into z to the power of minus 1 plus b1, yk minus 1 is yz into z to the power of minus 1. That's it. This is a z transformed equation. So I push yz term on this side, yz into yz minus b1 yz into z to the power of minus 1 equal to a naught uz plus a1 uz z to the power of minus 1. So now I can get the transfer function yz by uz, which is equal to a naught plus a1 z to the power of minus 1 divided by 1 minus b1 z to the power of minus 1. You can take out the z terms common and express it in this fashion, pole 0 fashion. So if I take out z to the power of minus 1, a naught into z plus a1 divided by z minus b1. So this is in the pole 0 form. So it has a pole at z is equal to b1. It has a 0 at z is equal to a1 by a naught. If I take out a naught, you will see that the 0 is at z equal to a1 by a naught. So this is the transfer function in pole 0 form. This is the transfer function in the unit delay form. So you should be able to get in and out of the time domain and the Z transform domain easily, and that is why this snapshot equation of a filter in the discrete domain will help a lot. Canonical forms. Let us discuss about this. This is an important topic. We need to relook at the filter block diagrams, FIR and IIR filter block diagrams, and see if we can rearrange the blocks to a standard structure called the canonical form. And why should we do that? So let's discuss and have a look at a typical. I will take a first order system as an example first. So you see that I have a unit delay block, and this is where we give the discrete time input. Let me tap out here and then put the scaling factors, and then use a summer, and I will add up these signals. So this is typically the FIR filter, which is a subset of the overall bigger IIR filter structure topology. Let me include the IIR structure also. So A0, A1, these are the scale factors, UN, YN, and let me take the feedback, pass it through another unit delay block, and have a scale factor B1 here, connect it in this way. So if you see the arrows, the signal flows in this direction through the A0, through the unit delay A1, and take the feedback through the unit delay block and to the summer. So this is the first order IIR filter. So when you say first order, it means that there should be only one energy storage element. But here you have two energy storage elements. So how can it be first order? Is it second order? That is the question. But actually this is a first order. You need only one energy storage element. So that is where the standard forms come in, the canonical forms. This block diagram, which I have right now written on this page, is very useful for understanding the concept, but this is not the block diagram that you would use for implementation. You would use one of the standard or canonical forms for implementation, because in this you will see that even though it's a first order system, I need to allocate two data memory spaces. So in the data memory in your program will be double. So therefore you need to do the rearrangement. So what does it mean? So just look at this. Let us go through the process for this first order. Then it becomes much more simple for any higher orders. So let me split at this point. I will split this, the summer. So I will have one more summer. So without loss of generality, this is still the same block diagram. I have made a split. So the split is, on one side I am having only the feedback part, and the other side here I am having only the feed forward part. So that is the division. So let me divide that, and let me have the nodes. This is an important node 1, this is another important node 2, and this is another important node 3. This is called UN, this is YN, and I will call this one as VN. So if you look at this part, this is an FIR filter. So let us say I want to have the transfer function of Vz by Uz. So which is, we know that this is A0 plus A1 into Z to the power of minus 1. So this is the transfer function. And on this side, we can take the transfer function of Yz by Vz. And this is the IIR part. So 1 by 1 minus B1 into Z to the power of minus 1. So this is the transfer function of this part. So now the transfer function, the entire transfer function is Yz by Uz. So which can be written as Vz by Uz, the feed forward part, into Yz by Vz, which is the feedback part. So I can write it A0 plus A1 into Z to the power of minus 1 by 1, that is this part of the transfer function, into this part 1 divided by 1 minus B1 Z to the power of minus 1. So this would be the overall transfer function. Now you see that I can interchange these two without loss of generality. There will be no change. Right? I can place it at this point, and this I can place it first like this, Yz by Vz into Vz by Uz. Still there is no change, it is the same system, and I can write it this way, 1 minus B1 Z to the power of minus 1 into A0 plus A1 Z to the power of minus 1 by 1, and write this in this fashion also, both are same. So therefore, I can also do an interchange between this set of block and this set of block without loss of generality. So these two I can interchange. So let me do that. So let me copy this, make some space, and do the splitting. So let me make the cut here, and let me make that space, and let me make the interchange. Right? So this is the interchange. This is the first part. This was the feed forward part, which I have put it later, and this was the feedback part, which I will put it later here. So UN will now be, input stream will be now given here. Output of this will be given to this part, and you take the output here at 2. The system is exactly same as before, same as this. So let me push that up, and let me rewrite this. So you have the sigma summer, you have UN here, the input, discrete input stream. Now I will draw this line. I'm going to draw this line and take this root A0. The A0 is going to the summer. I'll use the summer block, and that goes to YN. And from here I am going to pick off, pass it through a unit delay, and back to the summer. So I will pass it through a unit delay and have a scaling factor B1 and to the summer. So this part is now read on. Now from here, see, from here I have to have this root. So from here I will pass it through a unit delay block, then pass it through A1 to the summer, and that part is get completed. So I will call this one as VN here. So now if you look at this block diagram, this is Vn. So if I take some instant of time Vkt, if this is Vk, this value here after the unit delay would contain the one sample time previous value of Vk, which means Vk minus 1. Whatever the value of Vk was at k minus 1, whatever the value of V was at k minus 1 would be the value available here. So if this is Vk, this will be Vk minus 1. Likewise, this is also Vk minus 1. So I don't need two blocks. These two blocks can be clubbed together because they are giving the same value, Vk minus 1 and Vk minus 1. So essentially it becomes a single memory block. So I will club them together. So now you have Vk minus 1, and that is what is applied to this. I can bring in B1 here and A1 here. I am trying to put them in a standardized form. So this is B1 and this is A1. Now this is the filter. This is the first order filter, which is actually same as this. Exactly same as this. So this is the first order filter which is normally implemented because you need only one memory location in the data memory space of your program. But this is much more intuitive, especially understanding the concept. This block diagram is more intuitive, but while implementing, this is more optimal in terms of data memory usage, and we will use this. So if I have a second order system, you can just keep adding orders in this fashion. So let us say this can keep growing, z to the power of minus 1, any number of delays, and that will get added to the summer block actually. So this will keep extending. I will show this in greater detail for a generalized system, but this is the key takeaway of standardizing the filter, the IIR filter. This is the first order IIR filter, and the various parameters A0, B1, A1 are the design parameters that you need to design. And also note that in this canonical form you will see that there is only, if I say it's a first order, then there is only one memory element for that. So there are two variants of the canonical form. In the literature, you will see one is called the Control Canonical Form and the Observer Canonical Form. Both are used, both can be used. I will describe both the canonical forms in a generic way, but keep this in mind internally what is happening to the structure. Let us now write down the discrete equation for this canonical form at some snapshot instant of time. So let that snapshot instant of time be kt, and first define the variable at the output of the unit step, meaning first define the memory variables, because they are the state values, they remember, right? So always define the memory variables first. So I will say, I will call this variable here as v of k. So I will call this as v of k. So if this is v of k, what should be this variable? This should be v at k plus 1, the next state value, because this is a delay block. If this is v of k, this should be vk plus 1, right? So I will set this as uk and yk. So at that instant of time, kt. What is v of k plus 1? Let us write it down. V of k plus 1 is the next state. Next state, which is given by v of k into b1 will come here. b1 into v of k. uk will also add up there plus uk. So this is the state equation which gives the next state value of the state variable. In this case, the state variable is the output of the unit delay block. Now, the output yk is a naught v of k plus 1 plus a1 into vk. vk plus 1 can be expressed in terms of the state variable values at time k by this one. I can substitute here. This is called the output equation. Now see that I can generalize by making this a matrix. So let's say this is a matrix. This is a matrix of state variables, let us say, at instant k plus 1. So this is a matrix of the scalar values. This is a matrix of the state variable at instant k. This is a matrix for scaling the input. Okay. So in a more general term for state equation, this matrix is called the A matrix. This matrix is called the B matrix. Likewise, for the output equation, I will write Vk plus 1 in terms of all the state variables. So B1 V of k plus A0 uk plus A1 Vk. So y of k can be written as A1 plus A0 B1 V of k plus A0 uk. So if I say that the output equation, matrix of the output, so I have another matrix here, and this will be the matrix of the state vector. This is the state vector at instant k plus another matrix here which scales the input vector, direct feed through. So this is in state equation modeling parlance, this is called C, and this is called D. The state variable vectors are called X, right? So if I write this generic equation, it will be of the form xk plus 1, state vectors at k plus 1 equals A matrix, state vector at instant k plus B matrix, and input vector at k, then y at k equals C into state vector at k plus D into input vector at k instant. So this is the generic state equation. In the discrete domain, this is the state equation or the next state equation that you may call as the model of this particular system. So these two equations together will form the model of this filter. Yeah, if you can either use the transfer function or you can use the state equation model. State equation model is a much more better model to use, because transfer function makes the assumption of linear time invariance and also that the initial conditions are 0, whereas the state equations doesn't make that assumption. So let me go back to the infinite impulse response filter transfer function that we had discussed before. and explore the canonical form with respect to the generic filter. So if you look at the transfer function, the relationship between yz, uz, as we discussed, it is of this form. So you have the various uz's and the various scaling factors b1 to bn for the feedback term, where yz is the z transform of the output variable yn. Now I can rewrite this in this form. I can pick up all these yz terms, put it onto the left hand side, and take out yz as a common term, and then bring it down to the denominator on the right, and all the terms uz is a common factor, and bring those terms to the denominator on the left side. So yz by this equal to uz by these terms. Let's say it's equal to some wz. Now from this formulation, uz will be equal to wz into all these terms. So 1 minus b1z to the power of minus 1 to bnz to the power of minus n into wz is uz. So wz, so if I expand this, you will see that there is a wz term, 1 into wz, and minus b1z to the power of minus 1 wz, so on, bn into wz into z to the power of minus n. So all these terms which are having the unit delay components, polynomials in z, that I will put them together. b1z to the power of minus 1 to bnz to the power of minus n into wz. I will take it to the uz side and then put it in this fashion. uz plus all these terms into wz will be equal to wz. Then take this one equal to wz. So yz is equal to a0 plus a1z to the power of minus 1 plus so on to amz to the power of minus m into wz. So this is the other equation that we have with us. So these two equations I am again rewriting here. One is wz is equal to uz plus b1z to the power of minus 1 so on into wz. Another output yz is a0 plus a1z to the power of minus 1, a2z to the power of minus 2 so on into wz. Now this is the intermediate variable, I will call it as. So let us use this first and then make the block diagram. So uz, so that I am going to put it un. Now that goes into a summer, there's a summing block, this whole thing plus un that gets added up. So all these terms can be obtained by using the delay blocks. So let me say that there is a wn. This represents the n domain value of the z transformed variable wz. So let me put some unit delay terms here. Z to the power of minus 1, I am going to tap off b1. So z to the power of minus 1, that value into b1, I will add it here, right? Then I will put one more z. So z to the power of minus 2, b2 will get added up there. So on, I will put n delay blocks. So this is the nth delay block, and I will scale it with Bn, this Bn, and add it there. So all this orange lines and the input added together will give you Wn. Then come to the output equation. Again, the output equation. So Wn into A0 into A0, then Wn pass it through a delay, add it, push it through an adder to get Yn, and I'm going to put a delay into A1 and then add it here. I'll put one more delay into A2 and add it there. Then so on m delays and put it to the output. So now all these, you will see that this is Wn and this is one delay, two delay, so on. All delays of the same variable Wn. So these two can be merged together. So I'll merge them. And this would be the optimized standardized form of an IIR filter, generic IIR filter. This is called the control canonical form. What it means is that the control input to this single point here will affect this state, will affect this state, will going to affect this state is going to affect this state. So a single input here is going to affect all the states, and therefore it's called the control canonical form in the literature. So there is another form. Okay, I'll start from this equation. So A0 uz, that is this one. Now An uz plus B1 yz, these two. So these two I will put it together, A1 uz plus B1 yz, z to the power of minus 1. Then A2 uz and B2 yz delayed by z to the power of minus 2, delayed by 2 sample times. So on, I will go on to An uz plus Bn yz to the power of z to the power of minus n. I am taking n terms. I have stopped here at m. I am taking n terms, n greater than m. So this is another form where you can look at it. So let us try to make a block diagram for this. So starting with Un is for this, right? And somewhere here you have the output Yn. I am going to place that there. Okay, I will put a summer, because all this are supposed to be added up. Now let me take this first term, A0. So uz into A0 through the summer goes to the output. Now each of these, now take this one, uz A1, so A1, and there is Yn, there is yz, B1. So both this I will add it up. So these two are added. I will pass it through a delay and then to the output. I will pass it through a delay and then to the output. Then I will take this term, A2 uz, B2 yz. Both I will add it I will put one more delay. So you will see that A2UZ, B2YZ adds up, passes through Z to the power of -1, passes through another Z to the power of -1, then to the output, Z to the power of -2. So 2 delays. So likewise, the nth term, I'll take ANUZ, BNYZ, add them, pass through n delays. This is delay 1, delay 2, so on to the nth delay, Z to the power of -n, and then output. So this is another way of looking at it. Here it is not the control canonical form. Here if I observe the last state here, this state is based on this state. This is another state. This is another state. This state will dictate this state, and from this state you can observe this state, so on. You can cascade. The last state you can observe all the information of the system. Therefore, it's called the observer canonical form, whatever you can observe at the output. So this will become a bit more clear if you put the state equation, if you write it in the state equation form. Let us do that. So take the control canonical form. This is the control canonical form, right? So now I'll have to mark the state variables. All the outputs of the memory elements will be state variables. X1, output of this, X2, output of this, X3, Xn, output of this. So these are the state variables. So let me have a state vector where I'll write X1, X2, X3, Xn, so on. Now this is at time k plus 1, at time instant of k plus 1t, k plus 1th t instant. So this is actually the next state based on all the values at kth instant. So you have the A matrix, and then I have the state vector at k instant of time. Then you will have the B matrix and uk at value of the input at kth instant of time. These are a value of the states, value of all the states at kth instant of time. This would be x, this would be x1 k plus 1, that is this. This would be x2 k plus 1 or equal to x1 k. Likewise, this would be xn k plus 1 or the previous output of the previous state variable. So you see that they are connected. So let me write B1. So this equation x1 k plus 1, x1 k plus 1 is this. This is x1 k. This is x1 k plus 1, just like we did before, is equal to this plus this plus this plus this. So B1 x1 at k will get added up, B2 x2 at k, so on, Bn xn at k instant of time. So this will get added to give you plus uk, which is 1, will give you x1 k plus 1, that is here. So what is x2 k plus 1? The same as x1 k. So x1 k, all else 0, defines x2 k plus 1. Likewise, xn k plus 1 would be all zeros except the one before, right? Just like here, the xn minus 1th state will be 1. So this will be the state equation for the control canonical form. You see that all the scaling values come in the first row. What is the output equation? Y of k is nothing but, so this is C xk, x1, x2, xn plus d uk. So a1 plus b1 a0. So b1 a0 plus a1, a2 plus b2 a0, a2 plus b2 a0 in this root, an plus bn a0, and a0 direct feed through a0 into un will be the, so this is the output equation. Now we take the observer canonical form. So if you look at the output equation here and look at the state equation of the control canonical form, observe this. Any input, control input, is felt by state x1, and that percolates. x1 becomes the input to x2, it will manipulate x2, which will manipulate x3, which will manipulate so on xn minus 1, which will manipulate through this xn. So therefore, one control input can control all the states, and therefore it's called the control canonical form. So coming to the observer canonical form, I'll call this one x1, x2, xn. So let us write down the state equation. x1, x2, xn at k plus 1. This is the next state equation. This is A matrix. You have the state vector at k instant of time plus B matrix plus uk. So let us write it down. x1 into b1, right? So x1 at k, so if this is x1k, this will be x1k plus 1. So that is an x1k plus 1. This value here equals value coming from here, value coming from here, and value coming from here, right? So x1, this state passes through like this to b1 and then appears here. So that's why b1 into x1. x2 is coming direct, so therefore it is 1. And u is coming through this. Now rest all is 0. So u is coming through this one, a1 to this point. And u is also coming through a0, goes like this, b1 and appearing here. So a1 plus b1, a0. Then x2 k plus 1, x2 k plus 1 is, this is x2 k, which is same as x1 k plus 1. This is x2 k plus 1, which is this plus this plus this, alright. So b2, so x1 into b2, right, and input, this is coming through here. So x3 would be the immediate preceding state, and x3 will come in here. That is why x3, I'm just putting it as 1 there. And the input is a2. This comes in here, and through this b2. That also gets, so a2 plus b2 a0, that also gets added up. So like that, you can get the state equation for the observer canonical form in this fashion. Output equation yk is nothing but the state equation, this plus this, right? So you have the state values plus This is C xk plus D uk. Now the first state x1k and all else 0. Then uk through a0 comes in there. This is a0. So you see that observing just this last state value x1 here will give you the output. So therefore it is called the observer canonical form.